Sodium hypochlorite is commonly used as a disinfectant or bleaching agent. In this example, we are asked to calculate the pH of an aqueous solution of 0.089 molar sodium hypochlorite. And we're given the Ka of hypochlorous acid as 4.0 times 10 to the minus 8. The strategy for these questions is first to identify the major species in solution, next to write the equilibrium reaction for this acid-base reaction, then to write the ice table, and then find the expression for the equilibrium constant so that we can calculate the species of interest. Since sodium hypochlorite is a group 1 salt, we see that it dissociates completely into its component ions, the sodium plus 1 cation and the hypochlorite anion. The next step is to write the ICF table for this reaction. And here we see that we start with 0.089 molar sodium hypochlorite, which was given in the question, and we don't have any sodium plus 1 or hypochlorite anions to start with. Since the reaction goes to completion, we have a change of negative 0.089 molar for sodium hypochlorite and positive 0.089 molar for sodium and for hypochlorite, respectively. Next, we just have to add up the columns, and this gives us a final concentration of 0 for sodium hypochlorite, 0.089 for sodium plus 1, and 0.089 for hypochlorite. Now, taking a look at the ions present, we see that sodium is a conjugate acid of the strong base sodium hydroxide, and therefore sodium plus 1 is an infinitely weak acid. And therefore sodium plus 1 is neutral and does not contribute to the acid-base properties of the solution. Next, looking at hypochlorite, we can see that it is the conjugate base of the weak acid, hypochlorous acid, and therefore hypochlorite is a weak base. So this essentially comes down to a weak base problem. And so we will write the equilibrium reaction for the weak base hypochlorite. So hypochlorite plus water will react to produce hypochlorous acid plus hydroxide. Here we see that hypochlorite is basic as it produces hydroxide ions. So this is now an equilibrium problem, and we will have to fill in the ice table. Starting with the initial concentration of hypochlorite, we see that the initial concentration of hypochlorite is therefore 0.089 molar. Water is a pure solvent, so we don't have to worry about it in the ice table. And initially, we start with 0 concentration of hypochlorous acid and 0 concentration of hydroxide. Since the reaction is in equilibrium, we don't know exactly how far the equilibrium will shift, and so the change in concentration will be negative X on the reactant side and positive X on the product side. Adding the columns together gives us 0.089 minus X for the equilibrium concentration of hypochlorite, X for the equilibrium concentration of hypochlorous acid, and X for the equilibrium concentration of hydroxide. So this last line here, the equilibrium concentrations, is the line we will use to calculate the pH. So the next step is to write the equilibrium expression for the weak base reaction shown on the previous slide, and the equilibrium expression for hypochlorite is Kb, the base dissociation constant, equals the concentration of the weak acid times the concentration of hydroxide divided by the concentration of the weak base. Now, this expression requires Kb. However, we were given the Ka of the acid form, which was hypochlorous acid. But that's okay because we can easily convert between Ka and Kb using this expression. So plugging in the value for Kw and the value for Ka for hypochlorous acid, we have 1.0 times 10 to the minus 14 divided by 4.0 times 10 to the minus 8. And plugging this into our calculator gives us a Kb of 2.5 times 10 to the negative 7. And this is the value we can plug in for the equilibrium constant for our weak base. So doing the substitutions, we have 2.5 times 10 to the 9 is 7 equals X for the concentration of hypochlorous acid, X for the concentration of hydroxide, divided by 0.089 minus X, which is the concentration for hypochlorite. Next, we just have to solve for X, and we can do this using the quadratic formula. So rearranging this into the quadratic equation gives us this expression, and then using the quadratic formula will allow us to solve for X. Plugging these numbers in to the quadratic formula, we see that the quadratic formula will give us two answers because we have plus and minus. However, we should acknowledge that we cannot have a negative concentration, and so we only have to calculate the positive square root. In this case, A equals 1, B equals 2.5 times 10 to the negative 7, and C is the product of 0.089 and 2.5 times 10 to the negative 7. So plugging these values into the quadratic formula gives us a value of X equals 1.49 times 10 to the negative 4. And as you may recall, X is the concentration of hydroxide. And next we can calculate the pOH of the sample using the equation for pOH. And this gives us a pOH of 3.826. And finally, we can now calculate the pH. And the pH of our sample is therefore 10.17. Rounding gives us a final pH of 10.17.